we need to discuss choosing the right number of components when we're using the Gaussian mixture model. When using k-means, we use an elbow plot analysis. We measure the inertia as a function number of clusters, and we look for the point where the inertia isn't dropping so much, so that was our cutoff. We said, okay, that's the number of clusters we're going to use. And we understand there's going to be some interpretation, some subjectivity in the right number of clusters we choose, but we always need to back up our answer. When someone asks, why do we choose those number of clusters? Well, we can go back and refer to them to the elbow plot. And we said, okay, we measured when the inertia has reduced 90% of the initial one, or 95, whatever we choose, and that's how we choose the number of clusters. Or perhaps there's some other external constraints that are going to impose on us to consider our choice number of clusters. So can we do something similar with a Gaussian mixture model? Can we generate something similar to the elbow plot analysis to choose the right number of components, as they're called in the algorithm? So we could use inertia, but are there any concerns with using inertia when we're using the Gaussian mixture model? And we should be concerned about using inertia. That was one of the motivations of why we decided to talk about Gaussian mixture models. Inertia is basically the sum of distances of all the points in a cluster. And we understand that that's going to strive for isotropic clusters. But it's not going to strive for elongated clusters. In other words, the inertia score for an elongated cluster is going to be very high compared to one that's dense and isotropic. Let's think about it. If we go back to this image here, in this cluster, the distance between this point here to the centroid is going to be very large because it's an elongated shape. We don't want to penalize for these elongated shapes. We understand that we want to capture these elongated shapes. So inertia is not a good metric. So what can we use when we try to choose the right number of clusters for the Gaussian mixture model? Remember what the objective function was for the Gaussian mixture model? Remember, we're trying to minimize or maximize this function by adjusting the parameters. If we go back up here, we were trying to maximize the likelihood function, the product of all the probabilities of all our training points. We're trying to maximize that probability by adjusting the weights of each Gaussian, the location, the mean, which is another name for the location, and the covariance matrix. So all those parameters, all those degrees of freedom we have to manipulate, and we'd use an algorithm. When I say we, scikit-learn is using an algorithm to best fit, to best choose the model parameters, to have the largest likelihood function, to maximize that likelihood function. So it makes sense that we would use this likelihood function as a guide to decide what's the number of components. How many Gaussians should we use for our data set? Just like for the k-means, we used inertia to decide the number of clusters, or we're going to use the likelihood for the number of clusters. But before we plot this out, one of the things we'll realize is, well, let me first ask you this, is what do you expect that trend to be? How do you think the likelihood is going to look like as I increase the number of components? And since the likelihood is going to be a very small number, oftentimes we deal with the log likelihood, so the log of the likelihood value. And that's typically going to be a negative number. So any anticipations on how this curve will behave? Well, we should see something kind of very similar to the elbow plot analysis. Whereas we increase the number of components, basically the clusters, the likelihood function is going to increase. And this right here is we're applying the log likelihood. So one way people like to use to choose the number of clusters is by doing a holdout set, doing a train test split, where we train the model on the training set and we measure the log likelihood for the training set, but we also measure the log likelihood for some validation set, for some test set. And we see how that curve behaves. In other words, we might have something like this and then something like this. And that's the point. This is going to be the guide for the number of clusters to choose. That's one way people like to use to choose the number of components for the Gaussian mixture model. There's also another metric people like to use that we haven't talked about, so I'll mention here, is called the BIC, the Bayesian Information Criteria. And this BIC score is simply going to be equal to -2, the log of the likelihood, plus k times log of n, where n is the number of observations. K here is going to represent the number of parameters that we have in our model. So as it increase the number of clusters, the number of components, we're going to increase the number of parameters that we need to fit to the model. And this BIC here is basically saying, yes, you want to increase the log likelihood, but there will be a penalty as you increase the complexity of the model. That's what this term here represents, the penalty for having more and more components, more and more Gaussians in your model. So let's do this. Let's try this out. Let's figure out, let's choose, let's see if we can guide and know how many clusters to use, how many components to choose for a data set using the Gaussian mixture model. So we'll continue to use the California housing data set. So I'm going to define a function here, just like I did before, that's going to generate these plots for my analysis. I'm going to call this, define it as plot GMM, I don't know, just call it plot GMM. It's going to accept a training set and a test set. Okay, let's go ahead and define our scalar here. So let's define our scalar. Just got to make sure we scale the data. Let's go ahead and scale the data. Fit and transform of x of train. I think what I'll go ahead and do, I'll just go ahead and call that x of train. Make sure I scale the test. Okay. Let's define the range and the number of clusters to use. So let's just do 2 from 60, spacings of 1. And let's generate some lists here. Create some empty lists that we're going to store the log likelihoods. So one for the training set and one for the test set. And let's iterate through the number of clusters for n in n clusters. I know they call them components, but sometimes it's nice to call them clusters. So let's create that GMM object. Gaussian mixture model. N components equals n. The covariance type, say the full covariance. Let's go ahead and fit on the training set. And when we use, let's see, a log like a train, with the GMM object, the score method is going to return to us the log likelihood. So that's convenient. I can just calculate it by using the score method. And then likelihood test.append, I'm going to pass it to the score method of the test set. Okay, pass the test set to the score method and append the result. And we also want to calculate this BIC, this Bayesian Information Criteria. Luckily for us, let's first define an empty list to store those values. Luckily for us, there already is a method of the GMM object that's going to calculate the BIC. Right, it's a common thing people want to do when they're dealing with Gaussian mixture models. It makes sense that scikit-learn provide us a method to do this. So it's pretty easy. So we just do GMM, the name of the object. The method's called BIC, and we pass the data set. So we're going to pass the training set. We're going to calculate the BIC for the training set. Okay, and let's go ahead and generate our results. We want to plot these things on the same figure, 2 different axes for the y label. So we're going to use matplotlib. We're going to use the object-oriented API for this. So it's going to generate our subplots there. And for axis 1, we're going to plot the log likelihood of the train. And then from there, we're also going to plot in clusters the log likelihood of the test. Let's set the labels so we can better see. Okay, X label. As always, it helps that I spell these things correctly. Clusters. And set the Y label to log likelihood. Oops, I meant AX1. And let's set the legend so we can know what is what. Train and test. And AX2. And create a new axis based upon the previous one. And then let's go ahead and put a plot on that. And this one we're going to plot the BIC score. The Y label here is going to be called BIC. And when I plot it, let's see. Let me change the color to, let me say green. Let's flesh out the plot there. So we'll do tight layout, and let's, yeah, I think that's it. Alright, so that should generate my plot. And I'm going to be a bit impatient, so I'm going to just say print n. Sometimes this might take a while, so it's nice to get some progress. Alright, so this will shuffle the data. So here, let's go ahead and use 5,000 points. Get something more interesting that way. And then let's see, some 5,000 all the way to 7,000. So we have 5,000 points for the training and 2,000 points for the testing. You can always adjust that later, whatever you see fit, but I think this is a good choice for right now just to get something. Alright, let's see this works. Plot silhouette, of course, I'm using the wrong function here, so I'll just adjust that. I think I called it GMM. Let's run that. Okay. Notice it's slowing down, right? This is a nice thing why I want to print this out. It's very quick when we had a very few number of components, but it starts slowing down. That's one of the disadvantages of the Gaussian mixture model. It's not going to scale when we have a very large number of clusters. It's going to take a long time to train because guess what? We have more components to fit. All right, so we're at 37, 38. So yeah, so I recommend if you have time, try it out. Play around with running the Gaussian mixture model and running the k-means. You'll notice, yes, maybe at first using the Gaussian mixture models is faster to train, but you might have a small data set, small number of clusters or components. But as you scale up, then you're going to see a big hurt in performance. I want to point out here, always look at the documentation. So in scikit-learn, we see in their documentation the pros and cons with the Gaussian mixture model. And in there, when we're talking about the number of components, they talk about basically what I discussed here. Doing a holdout set, train test split, or using the BIC. So we're going to use both methods, and we're going to see which one is the best number of clusters to use for both methods. Using the BIC and using a train test split, looking at the log likelihood. Okay, let's see. Come on. Of course, knowing me, it's probably raised an error at the very end. I had some sort of typo. All right, moment of truth. All right, there it is. Okay. All right, so I probably chose slightly different colors. But we see here, so we either see the training set. So as we discussed before, as we increase the number of components, the log likelihood is going to keep on increasing, which makes sense. There's more Gaussians, so there's going to be a better job to increase to have a very large log likelihood. And what else do we have here? Okay, yeah, and this one here, this other green curve, is the log likelihood for the test set. So notice that also is going to increase, but at a certain point it starts to plateau, starts to oscillate, and it starts to drop as we increase the number of components. So given this analysis here, it looks like we should choose maybe no more than 25, no more than 30 for sure. Perhaps you want to stick anywhere from the 20-25 range as a number of clusters to use for this data set. Let's look at the BIC. Let's see what the BIC tells us. In this case, we're going to look for the lowest BIC. So the BIC drops, and it plateaus, and then it starts to come up again. So it looks like, given this analysis, the lowest value for BIC is about 30. And in fact, this plateau region is going to extend anywhere from 20 to 30. So using BIC suggests using 20 to 30, and using the log likelihood says use 20 to 25. So yes, not the same answer, but a pretty decent overlap. So we can use this to guide our choice of the number of components we use for the Gaussian mixture model.